As Krista says, I'm from a team at the University of Cambridge. We started up a project called LowRISC to, the aim is to produce a fully open source SoC, and of course, we're doing that using the RISC-V instruction set architecture. So our aim is not just to design this, release the code, but importantly to actually produce production silicon in volume. We started last summer as a non-profit project. So to give a little bit of background about where we're coming from, so there's Rob Mullins, who's leading this at Cambridge, was one of the co-founders of Raspberry Pi Foundation. I was involved since we had alpha boards doing lots of work on software, operating system stuff. So we have a background from obviously low-cost computing through that, and we had an ex-lab member who came to us and said, why isn't there an open source system on chip yet? And aside from just wanting this to happen, he also had some personal resources in order to provide funding to help us get off the ground and make that happen. And so this has been kind of how what led into this project. And I mean, more generally, our motivations are in many ways similar to the motivations to the Berkeley team at RISC-V, in that something like this is important and useful for teaching, for research, for things such as transitioning ideas from research to production use, but also allowing researchers to work and make changes to something which approximates a real shipping system, rather than trying to work out what AMD and Intel are actually shipping and working with very coarse-grained simulations of what they have. Another reason is that there's also we're finding, particularly the more we've talked about this, a lot of people from industry, people who in the past may have had very good, close relationships with various vendors, who are finding that, as the volume has gone up, they're much more interested in smartphone SoCs, but they're not able to get the same flexibility in licensing and making the changes that they need. And importantly, what they want is something where they can make some changes, but there's a tried and tested base. And as I kind of point out here, this is of course very important for startups and innovation in the industry. What we're trying to produce would be so that if you want to create a new semiconductor startup, you have a full, well-tested, well-documented, known working system on chip on which to build upon. You don't need to go through complex, time-consuming, often difficult licensing, not to mention expensive licensing negotiations for the core intellectual property. So you can focus on the accelerator or the particular new mechanism that people are hoping to add. And of course, this benefits people across the whole industry, including the established big players who rely on this pipeline of startups coming through the system in order to actually get new product ideas and new developments out there. And so some of the opportunity we see is that we're doing this from scratch. We don't need to, there are no existing customers to support. We don't have the same backwards compatibility concerns that one of the existing players does. So we have this opportunity to do a clean slate design, to re-question the way some things are done, and to try and provide some more flexible, reusable components rather than something which is fixed. I mean, as Chris has been saying, the technology scaling is slowing, which means that we can be more competitive with people who are at the very bleeding edge in terms of technology, and also means that our investment in a certain process can be amortized over a longer period of time. And also with the way things are, the cores that we're instantiating, particularly the small, 3-4 stage pipeline cores, are so tiny on a 28 nanometer process, they're effectively free. And of course, given we're talking about RISC-V, they're also free in terms of licensing cost and so on. We also have no need to produce a range of products, so there's no need to hold back certain protocols for the high-end version in order to produce a nice product line where we have some low margin part at the bottom end of that and a high margin part at the end. And there's also, I think, a real opportunity to work with the open source community. Particularly, I think there's a lot of potential for collaboration with the open source software community for cross-pollination of ideas and optimizations across the whole stack, where I think a lot of people have been saying for a long time, wouldn't it be great if hardware designers could do this? Well, now, in a sense, anybody can at least contribute and see in more detail what hardware designers do, what constraints they're up against, and make more meaningful assertions or contributions. Now, our approach is to, as I'll explain with the two features that we've been focusing on most recently, is to provide everything we do, we look to provide a simple, reusable piece of functionality rather than just trying to locate a problem and solve it with a specific single-purpose solution. I should also say that we're deriving from Berkeley's work on the Rocket SoC generator, so we're building upon that and adding our various other features and other SoC functionality. We also, given that we're aiming to produce production silicon, we're not, but we're also at university, so we're partially a research project, partially people who just want to see open source hardware happen, but it's also a product development type of process in that we have to produce something that people in some tens to hundreds of thousands would actually want to purchase. And so although there's a small hardcore would purchase something that is almost like for like with an existing ARM or MIPS processor, but really we need to provide something which is interesting on top of that, which is where some of the features like Minion Cores and tagged memory come in. We're trying to develop out in the open as much as possible. It's kind of early days for the project, so there's a limited amount out there. We were initially a bit worried about announcing our intentions, what we're working on as early as we did, but we've actually found that the number of people who've come back to us with offers of help or advice, it's shown that it's helped us move forward far faster than we would have done otherwise if we'd kept things to ourselves and just waited until everything was perfect and fully developed before sharing it with the world. And our initial, I should say, one of the obvious problems with open source hardware versus open source software is we don't have this nice property where you can duplicate it for zero cost. We don't have the Star Trek style replicators yet. And so one of the aspects of project that we hope will help appeal to a wider open source community will be that we hope to advertise multiple scheduled silicon runs. So people can contribute with the knowledge that what they are providing will be in a tape out in 18 months or 12 months or whatever it is at that time. And our initial volume target is something that looks not dissimilar to a Raspberry Pi in terms of small single board computer, probably with Wi-Fi, Bluetooth LE module, targeting the same, the hacker maker community that have bought into the Raspberry Pi before us. A kind of tongue-in-cheek Raspberry Pi for grown-ups, and we say this because it's it's the sort of thing that actually, if you're somebody who is studying computer science at university or has studied computer science at university, there's a lot more flexibility to do interesting things than there is on one of these existing platforms. And so a rough straw man architecture for our system on chip would look a little bit like this. So let's say we have 2 to 4 Rocket-based RISC-V cores with a fairly unsurprising L1 iCache Dcache connected to a coherent network. And the two things I'll be talking about are our tagged memory, which you can see part of here with the tag cache, and this section I'll talk about afterwards, which is our what Krista mentioned earlier, our ideas on I/O nodes, so software programmable I/O through the provisioning of these very small, very low cost RISC-V cores on chip. And so all tagged memory is associating metadata, so some small number of bits with each memory location. And our implementation approach is to interpose this tag cache in between the memory controller and your L2 cache to logically extend every 64-bit word to, let's say we have 2-bit tags to 66 bits. So the tag cache will keep a cache of the tags for each physical address and if you have a cache hit, it'll just stuff it into your cache line that you're loading in. Otherwise, you would have to do a separate memory read. So of course, having a high hit rate in your tag cache is quite important. But in practice, given that we have a small number of a small number of tag bits versus your actual cache line size, you get a very, very large reach even with a small cache. There we go. And our initial motivation in pursuing tagged memory was security, which is something that almost everybody we've spoken to who had feedback for the project has said is very interesting or important to them. We saw an opportunity to try and at least move a little bit ahead of what's currently offered in existing ISAs. And what it offers is the prevention of control flow hijacking attacks, be it a old school buffer overflow via code injection or return-oriented programming. All of these rely on the ability to overwrite a code pointer, say a return address or a vtable address. And so using the tagged memory, this allows you to provide a fine granularity, word granularity, read-only memory protection. And there's a lot more to say about this, but I'll have to point you to the memo we've released on our website, which goes into much more detail and about how you deal with use after freeze and a couple of other subtleties regarding that. And so, as I mentioned, we're kind of talking at the moment. It's a parameterizable thing that we'll be exploring as we work on this. But for now, we're thinking 2-bit tags, which gives you something like a 3% storage overhead, and we anticipate a similarly small, under 5% performance area overhead. And as I mentioned, part of our philosophy is to look at features which are generally reusable. So there's actually a whole range of other ways that you can make use of this tagged memory. What it gives you to your toolbox in order to create solutions is infinite hardware memory watch points, which combined with a low-cost interrupt mechanism means that you can layer on top of that arbitrarily complicated policies. So you do all the sort of things that debug tools such like address sanitizer and other tools which make use of shadow memory and then keeping extra metadata alongside just your tag bits. There's a potential to implement those more efficiently because you no longer need to intercept every single load and store operation. There's also other things such as garbage collection and look back at what was done with the list machines. We can mark things in memory just to indicate whether they are integers or pointers. It's a simple extension, and also there are interesting things we can do with regards to parallel concurrent programming. So you have the potential to, in the simplest case, just use them for per word locks without using extra memory. But we're also interested in looking at existing work on full empty bits, which could provide a very low cost synchronization mechanism. And so taking another look at this diagram, there's this Minion Core section which I mentioned previously. So we have say 4 to 8 Minion cores, which would operate at up to the core frequency of our application cores. Each of these are connected to local scratchpad memory for real-time, due to the fact that we want to do real-time I/O on these. And I'm showing it linked up to so the I/O network with a DMA controller for communicating with our coherent network. So these can write into, say, the L2 or L1 cache of the RISC-V cores, or directly to main memory to give you a trade-off of what level of cache coherence you want with your application cores. And we also have shown kind of here. This is just more traditional I/O controllers. So at the moment, we're talking about using these lightweight RISC-V cores to implement SPI, I2C, SDIO, your kind of low bandwidth communication protocols, because that's the kind of non-research bit of the project, in that we know plenty of SoCs do something very similar or have done in the past. But we're very interested in looking to see how far we can take this in terms of using USB, Ethernet, SATA, much more higher bandwidth protocols. And so as before, there are a number of ways we can make use of this. The soft peripheral use case that I've just mentioned, being probably the main one. And this is useful because as a small development team with limited budget, the fewer IP blocks we have to produce, verify, the better. It also means that we potentially a much wider contributor base in the sense that the number of people who can contribute even to quite low-level assembly designs versus actually write hardware is quite a lot larger. But there's also advantages, we think, in terms of power. Even if a specialized piece of IP might be slightly lower energy for your serial port or what have you, you do have the additional benefit of having additional logic closer to your I/O, which you very obviously could use to listen for incoming data, pre-process it, and only wake up your main power-hungry application cores when actually required. So wait on your Bluetooth connection and only bother waking up Linux once you actually have a meaningful request. This could also link together with the tagged memory idea we have. So assume that we have a low latency communication link between application cores and Minion cores, say a FIFO. We're imagining a Minion core could subscribe to events from that application core, say branch misses or accessing tagged memory addresses, and then you could implement your security policy and externalities on that Minion core off the main thread. There's also, of course, what these also give you is the ability to do a secure, physically isolated execution. So we are also interested in looking at ways of not just doing the obvious thing and protecting the application core from buggy device driver code, if you will, running on the Minions, but also providing security guarantees about memory which has been allocated to those Minions and the software that is running on them, where you might want to do perhaps very security critical calculations or computations. And I should say, just like tagged memory isn't a new idea, it goes back to the IBM mainframes list machine. This is something where we have examples from just about every decade since the 1960s with the CDC 6600. But we think the trade-offs make a lot of sense, particularly at right now where the cost of cores is so low. In terms of the architecture of Minion cores themselves, I've been talking about wanting to use them for I/O, and of course having predictable timing is essential for that. And I should also point out that this I/O Shim section is very important for providing the basic low-level stuff where it would just be really, really dumb to do low-level bit banging. So shift in, shift out, parallel load, all these sorts of operations where you're just wasting energy by doing it in a loop in your assembly code. So our project roadmap is looking like, well, tagged memory with a tagged memory implementation based on the Rocket core we're currently working on. We should have it out there hopefully in the next couple of weeks to a month. The Minion cores concept is an earlier stage of development. We'd hope to, again, release FPGA-ready code kind of middle of the year, second quarter. And we're aiming to tape out a dual or quad-core test chip towards the end of the year. So so at back of the lab, we have a separate research project, 128-core test chip we're taping out this summer. So once that's done, we're hoping to get this one through at either 28 or 40 nanometer with integrated memory PHY, Minions, and so on and so forth. And one of the things we found working on this is that the digital logic, so the things that we can synthesize and verify through the Synopsys tools, what have you, that's relatively easy to understand and work with, but it's actually the packaging constraints, worrying about integrating memory PHYs and other more analog-like IP are actually very time-consuming. We're grateful to all the people who've given advice so far, so we're seeing a workable route through to test chip and afterwards, and we're hoping that one of the ways we can help contribute to the wider community of people trying to do something similar is documenting and sharing what we do in order to make that process easier for other people to follow. And we then expect to see a volume run towards the end of 2016 or early 2017. So our next steps are obviously working with the wider RISC-V community on software work, compilers, Linux ports, etc., etc. We've been doing some work on documentation that we hope to upstream and share more widely. So Wei, who couldn't get a visa in time, unfortunately, has been working on working with the Rocket code, generating a whole bunch of diagrams and so on as he's understanding what works. So we're hoping we can help to contribute that back to make the process easier for other people who are trying to build on Rocket. We're interested in verification, formal methods. I should say one of the kind of initial, so to clarify our performance goal, our backer came to us and said he wants to be able to run Linux well, and so this is very much what we're aiming for. And to do that, we want to build on existing benchmarks and start looking at things which give a more realistic Linux workload. So we're thinking more of PostgreSQL scaling up to 4 cores, looking at things where you have a meaningful number of TLB misses. So in the future, we hope to be exploring those and analyzing how well they work out to move beyond for simple micro benchmarks. And I'm very interested in talking to anybody about programmable interrupt controllers, performance counters, debug, all these things which I expect many of us will have thoughts or ideas on in the breakout sessions and so on. Our final kind of side point is about us as a project and what it means to be successful for us. We want this to be a truly open source project in the sense that we have people outside of the core project contributing. The aim isn't to just be a cheap or free source of intellectual property. Eric S. Raymond did a very famous set of essays about the Cathedral and the Bazaar, these different models, but I'd say they all fit into basically these 3 cases where most projects probably start at this one and try and make their way to case 3, though some choose to stick here. So right now it's early days for us, so we will soon be putting out source, and early stage development often does tend to happen behind closed doors because that benevolent dictatorship thing tends to work very well for early stage design decisions. A place where a lot of projects get stuck is development happens in the open, but either nobody else cares or it's just there are other problems that stop people getting on board. But where we really want to be, which is where we saw the Raspberry Pi really take place, was when a substantial portion of development on the project is embarked upon by people outside of the core team. So we're getting meaningful contributions from people around the world, and we're starting to see a number of people who have been reaching out to us privately, discussions on our mailing list, and so on and so forth. So this is really what we're heading towards. And so if you want more details on the Minion Core, particularly the tagged memory, where there are quite a lot of subtleties that we detail in more, we give a little more detail on. We have a memo on our website, announcement list, discussion list, etc., etc. And obviously I'll be here the next couple of days. I'm very keen to speak to anybody who has ideas or experiences. And if you're lucky enough to be in Europe at the end of the month, then we'll have a low-risk talk at FOSDEM and probably a bunch of ensuing discussion around open source hardware, RISC-V and the like. And that's it. Does anybody have any questions?
Hi, I'm Tommy Thorne. Do you have any software model for executing your tagged memory?
Not currently. So currently we have our stuff kind of working in simulation on the Chisel code. We expect to release a modified version of Spike in the next few weeks, which would include that with a. We haven't finalized what the ISA interface for tagged memory should be, so we'd have a kind of dummy stand-in ISA interface. That's something that we hope to explore in more detail and discuss with the wider community.
Are you planning to modify the compiler for generating the tags, or?
Yeah, so in the kind of default, in this standard deployment, which meets the requirement, the initial motivation in order to protect against these control flow hijacking attacks, then yeah, we'd expect to share a modified compiler which adds the necessary extra instructions to set and verify that those bits are set.
So if the code is compiled for standard RISC-V,
yep,
that would not benefit this hard?
Correct, not unless there was extra metadata in your binary that allowed you to do some rewriting.
I read your memo, the one on the web,
yep,
and I think what's unclear there is the recursive problem, which is the tags protect misuse of, let's say, a return address pointer or something like that. But what protects the tags?
Well, I mean, So what protects for tags is that they are protected through the MMU from people arbitrarily writing to that area. You're right in that any user program can modify the tags. So once you've achieved arbitrary code execution, you could then modify the tags. You could imagine having modes where you need to be in supervisor mode to modify a certain tag. But yes, it's kind of one of the trade-offs would be we want to be able to make it very low cost to modify tags, because if we had to have a syscall in order to switch to supervisor mode every time, then that would put off a whole bunch of other potential use cases. But yes, for security, you'd be relying on the fact that you're protecting against arbitrary code execution. But once somebody if somebody managed to get arbitrary code execution, then yes, they could then modify tags or do whoever else knows what to your system, which is how things work.
You mentioned a number of exciting uses of tags.
Yep.
And you also said that you were initially going with 2 bits. Mm-hmm. Would you be able to support all those features with 2 bits, or would that require more bits?
So some of those it would be a trade-off in terms of, so you might use the basic 2 bits to support, to use them as infinite hardware watch points, so to watch a certain location in memory and trigger a low-cost user-level interrupt when it is read or written, and then say the Minion Core, or if you're sending it to a main core, would then have to update another out-of-band data structure. So there's this kind of trade-off that we'll hope to explore in terms of how many bits that you have, so that you can have a more low-cost way to store the metadata close to where it's required, versus just having this very basic 2 bits, but then having extra metadata you need stored elsewhere.
So isn't it pretty easy to make it variable, runtime configurable, how many bits you use?
Well, there's a runtime configurable, given that we're choosing to copy the bits up into the L1, L2 cache. There's some overhead there, but yes, we could make it so it is configurable.
This actually is going to be a far larger problem. I think RISC-V is a good opportunity to solve it, because we are essentially getting into a new kind of a trusted computing model, away from the MMU into tagged architectures. So it might be worthwhile to see how we can standardize it generically in RISC-V, what kind of tags, because you need language extensions, you need operating system extensions. So, the exercises that you're doing, that we're doing, they're all one-off experiments. But at some point of time, if this has to be generalized, then we got to make a call as to how we fold it back into a RISC-V supervisor extension, which is generic.
Dave Patterson from Berkeley. Do you have a biggest concern about RISC-V that's an obstacle for you being able to do what you want to do?
I think, certainly my biggest interest in this workshop is this issue of deciding how it's going to work as a foundation, how future developments of the ISA, the supervisor spec, etc. proceed. So I think working that out is kind of the highest priority, or the highest point of risk for us as a project.
Thank you. In years past, we looked at adding metadata bits over memory to implement transactional memory. And as we looked at other applications of the metadata, we had a similar concern about how do you compose these diverse aspects and lay them over. And we came up with an obvious idea of a metadata ID, or metadata context ID as a parameter to the get and set metadata instructions. So that would essentially allow you to set red metadata and green metadata, or different categories of metadata. You'd obviously have to manage this in your metadata cache and through those instructions, but then it would allow you to have separate subsystems all share basically different address spaces of metadata over the same physical addresses.
Yeah, I think it's definitely something we need to evaluate the potential overheads, because as you say, having these different kind of address space and metadata could have a very big payoff, and it may be a relatively low hardware overhead.
Zal Alam from University of Michigan. So my question is about the SoC. So what is the goal of the SoC? So as I can see, you have like 2 small cores.
Yep.
So you don't. So you think people wanna experiment with more complex cores? As I understand, the RISC-V core is a 5-stage pipeline. And also you don't have any like FPGA fabric, so that people can implement their own accelerator, since it's an SoC.
Yeah, good question. Yep. So the rocket that Berkeley generating is designed to be a dual issue dual issue pipelines. So it is at a certain point in the design space where you have less area, but actually quite decent performance. So it is, intended to be competitive with, as I've compared it against the Cortex A5, right, or the with A7, with and certainly with more work on TLB. Well, pushing up the size of TLBs, etc., you'd imagine it would be competitive with the Cortex A53. So it is at a kind of design point where people are, you can run Linux usefully, people are interested, and yeah, as other cores develop and if there's a decent out-of-order implementation comes along, we definitely look at using that. In terms of interfacing with external things, so custom development, to a certain extent, you can do your I/O level stuff on the Minion cores in software. What isn't shown here is where we'd have another interface for connecting either to another low-risk chip or indeed an FPGA. So you might imagine that one of our development boards would have an FPGA on the side. You have a high bandwidth, low latency serial interconnect to it, and you can use that to implement your own accelerators or experiment with future hardware changes.
Okay, thanks. So one of the most important things we find about meetings are the breaks. So there's a half-hour break now for you all to interact with each other. We'll get back at 3:15, and Nick will tell us about what's happening in RISC-V at BlueSpec.